All right, this is Further Stats 1 from 2023. Let's just do it. We can see immediately from here that this row just means that this plus this plus this plus this plus this equals 1, obviously. So that turns into this, which turns this. That's going to be helpful for later. For now, expected value of x is, of course, this times this plus this times this plus this, and so on. Now that, when you look at it, it thinks, well, you can't do that without a and b, but because the a's cancel and the b isn't there in the first place, that just gets you a number, which is nice. And then it says variance is this. The variance is the e of x squared minus e of x all squared. So e of x squared means this thing squared times this, plus this thing squared times this, plus this thing squared times this, and so on. So I'm going to do that, and then I'm just going to take away this minus 0.4 squared. So that's just squaring the value that we got there. You end up with this, which we can tidy up into this, I guess. Well, we can't tidy up, it's just part of a's. So a equals that, and then we can put a back into here, and we'll get b as that. Now it says we're doing this twice, essentially. Find the probability that we're bigger than 3. So if we took a 1 first and then a 3, or a 3 first and then a 1, or 2 3s, that's the only way to make the sum of them bigger than 3. The moment you take a 0, you can't end up bigger than 3, because the biggest you can take from another thing is 3, and likewise down here. So it's either a 1 and 3, 3 and 1, or 3 and 3. So the probability of getting a 1 on the first is a, and a 3 on the second is 0.3, so that's going to be 0.3a. And then likewise, a 3 and a 1 is also just going to be 0.3a, and then getting 2 3s is just 0.3 times 0.3, because you just need it to happen twice. And yeah, at this point, I think I remember at some point that a is equal to 0.18, so you put that in, and you get the answer of 0.198. And that's the first question done. We've got the Poisson question here, so average of 1.7, so h naught, I guess, is that lambda is 1.7, and h1 is that it's changed, so it's not 1.7. Now we're going to model this over 10 minutes, so we're going to times this by 10 to get 17. And now we just need to think about what the probability of getting more than or equal to 25 causes, I guess, which is, of course, when you actually want to calculate that, the same as getting 1 minus x less than or equal to 24. And we type that into a calculator, we get this. And yeah, that is, I mean, it's less than 0.05, but remember, this is a two-tailed test. So we actually need it to be less than 0.025, which it isn't. So we're not in the critical region, and therefore we will accept h naught, or there's insufficient, say, put something to do with the context about rate of cause, I think is necessary for a final mark. So maybe I should have written here, accept h naught, insufficient evidence to say that it's changed. Maybe I should have said that, but I've said that out loud, so that's fine. 1.2% of the cause lasted longer than this, makes 70 cores. Well, this just looks like binomial now. N is 70, probability of 0.0012, I think. So that's cool. We want more than 2 of them, so we're looking for probability that y is more than 2. That's 1 minus the probability that's less than or equal to 1. Or sorry, less than or equal to 2, because it's not equal to here, of course. Type that into a calculator and you get this here. The last part of this question is quite interesting. 95% of days have at least 1 core lasting longer than this. Now, that doesn't tell you there on its own what the probability of 1 core lasting longer than 30 minutes is, because you don't know how many cores there are on a day, right? So we can use this information. 900 cores arrived, and none of them lasted longer than 30 minutes. We can use this information to help us, because we can say, let's set up a binomial with n being 900 and this unknown p-value that we're going to try and figure out. But we know that the probability, firstly, it says estimate, right? So we're going to estimate this to be a Poisson, so that's just going to be np in for lambda, so that's 900p on our Poisson. But we know that the probability of this being 0, again, approximately, because this is an estimation, is 0.05, right? The probability that you get no calls lasting longer than this is 5% or 0.05. And now, of course, because we have this here, we know what the formula for Poisson looks like. It looks like this. And with x being 0, that just goes away because something squared 0 is 1. And so does this. It's just dividing by 1 as well. So it just ends up being e to the minus lambda, which is e to the minus 900p. And of course, we can solve this for p, and we'll end up with our answer there. I think I underlined those there just because everything is at least to 3 significant figures, it seems, in the mark scheme. It's the safest thing to do would just be to write everything on your calculator screen after every single question, basically. Good. So next thing, we have someone doing this thing. They write out the frequencies of different number of heads when flipping a coin 5 times. This person believes this distribution models it well, where you're just saying it's half. Now, of course, we can work out RNS either in a calculator by just using this binomial and typing in x is 0, or we can just say it's 0 to the power 5. It doesn't really matter. And likewise, this is 5, choose 2 times 0.5 to the 3 times 0.5 to the 2, or you just type it in the calculator. Of course, you also times both those by 170 because the calculator gets you the probability. You want the frequency or the expected frequency, so you times it by 170 because they're doing this for 170 days, and you get these two numbers. Of course, binomials are also symmetrical. When you do them like this, obviously if p is a half that, I should say, then binomials are symmetrical, so therefore we can just use the same two numbers there. And we'll get this. Now it says carry out a suitable test. So firstly, we'll just say, I guess, H0 is this, H1 is this. So H0 is saying this is suitable, H1 is saying it's not suitable. And yeah, that's my hypothesis. The test is against critical value. So we're going to use this formula here. This isn't in the formula sheet. There is a similar one in the sheet, but I like using this. I think it's the easiest way to do it by hand. You do this thing squared minus the, over this, plus this thing squared over this, plus this thing squared over this, and so on, and then just take away n, which in our case is 170. Before you do that, you do need to make sure that none of these values are below 5, but they're not, so I'm just allowed to go straight in with this and calculate that value, which is this. And now I also have degrees of freedom. There are 6 columns here, but they all have to add up to 170, so that's one restriction. So 6 minus 1 is 5. Just make a note. We're about to use this. I talked about it here, though, as well. It says if it's calculated, and that's a restriction. This hasn't been calculated because he's just estimating that this could be quite an good idea. He has calculated these numbers, but because this entire model has been based on an estimate, that's not the calculation there. It's if the model has been made using proper maths, then it's a restriction. But this has just been done by guesswork. He's just saying maybe it's a half. So that doesn't count as calculation. So it's just 6 minus 1 equals 5 for our degrees of freedom. Now, of course, we can look in the table. I don't know why that came up first. If we look in the table, our chi-squared table, with degrees of freedom 5, and looking for 0.005 because it's 5% significance, we're just going to find this number here. Our number was much bigger than that, so this is a significant result, and that model is not suitable. We can kind of tell that, right? Because all these numbers are skewed towards this end. It's probably not a half. It's probably bigger than that. Nima believes that it is bigger than that. She believes it would be better if she used a different value of p. Now, this is not the easiest single mark question in the world. What I did was I wrote the probabilities underneath here. So I said the probability was just everything over 170, essentially. And then for a binomial, the expected value is just np. For example, if you have a binomial with 100 tries and p is a half, the expected value is 50, right? But also the expected value, as we saw in question 1, is this times this, plus this times this, plus this times this, plus this times this, and so on. So we can set that np, which in our case, n is 5, right? You're doing it 5 times. 5p is equal to this whole thing, which is 498 over 170. And then divide by 5, and we end up with p as this. So again, not the easiest single mark. I'm not sure whether there was a more obvious way of doing that I didn't spot, but that would be the way to do that that I got. And then, okay, so that's our value of p. And remember, what I was saying in the previous part of this question, that is a calculated value of p. Right? We've looked at the actual stuff we've got, and we've calculated a suitable p for this distribution that we're attempting to use here to make this look the same. So therefore, that's another restriction. So this time, and also what I said before, of course, if one of these is less than 5, then you also need to get rid of it and shove it into this group here. So that's what I'm going to do. I'm going to shove this 2.07 into here and make this group either 0 or 1. That also means I need to collapse this group as well and make that a 13, just because I need the groups to match. Otherwise, the OI over, or EI over OI squared, whatever it is, that wouldn't work if you have a different number of columns. Although actually we don't need to do that because it just says it's 1.62, so we actually don't need to do that ourselves. But anyway, we now only have 1, 2, 3, 4, 5 columns. We have the restriction that they still need to add up to make 170, and we also have the restriction because that p-value was calculated doing some sensible maths and not just a guesswork. So we're only down to 3 degrees of freedom now. The critical value, if we look in the table for 3 degrees of freedom and 0.05 again, I think is what we're using, is this, and her value is way less than that. So it's a very good model. So it's not in the critical region. It's a very good model. And so p is very likely bigger than 0.5, I guess, is what I've said here. Oh, hang on, now I'm answering this question here, aren't I? Sorry, with reference to the model, comment on the probability of it landing on heads. Because Nima's model is so good, it's very likely p is bigger than a half, is what I said. And then the independence of the spins of the coin. Well, because the binomial estimated this very well, and the binomial needs independence, that means it's very likely that this has independence as well, is something that you can also say about that. I think that's how it works anyway. Question number 4, there are 32 students in class. Each student rolls a fair dice. and stopping when the total number of sixes gets to a 4. Now, we should recognize this kind of thing as a negative binomial. I've already put all the information about negative binomials from the formula book down here. You don't need to memorize any of this. It's in a little table. So we can say we've got a negative binomial. This is R, this is P, where R is the kind of targets that you're going for, 4 of them, and P is the probability of getting each one, which is a sixth, of course, because it's rolling a dice. And what we can do with this is we can work out from this table, we can work out both the mean and the variance very easily, because R is 4 and P is a sixth. We can just do 4 divided by a sixth is 24 for the mean. And for the variance, likewise, a very simple calculation to type in gets you this here. And now when you're estimating a mean, that's a pretty big giveaway that you're doing the central limit theorem to do this kind of thing here. But we've got mu is 24 now, and we've got sigma squared is 120. N is 32. So we're going to put that 32 in there, and we end up with this normal distribution that we can use. And we're just going to ask, what's the probability of being in less than 27.2? And it's going to be this here if we type that into a calculator. And job is done for question 4. Question 5 then, so another one about distributions, I guess, and samples and things like that, testing things. That feels like we've done quite a lot of this already, but okay. Again, we'll say H naughts because we're doing a test here. So H0 is this, H1 is this. He's saying specifically it's less than 330, so we do need to see less than, and it's a one-tailed test, so we'll be looking for 0.05 later. We're going to do, again, because it's a sample here, we're going to use the same idea of sigma squared over n into our normal distribution, just like we saw before. So that's going to be 330 is the mean, obviously, and then sigma is, or sigma squared, sigma is 8, standard deviation 8. So sigma squared is 64, and then n is 25. And we'll just do it like this, and we'll get this, and then we will find the probability. So we want to know, because we're looking for the critical region, essentially I'm looking for the value on the normal distribution that would give me an area of 0.05 beneath it. So I want the probability of x less than some number being 0.05. You can just type that into calculator, right? Like it's the inverse area bit where you're looking for an area of 0.05 with these two numbers here. And you end up with this here, and you'll end up with your z value. So that's good to go. The director is concerned that actually it's doing it wrong both ends. So he wants to test this kind of idea. Find the type 1 error. So this is one of the only things that I would ever use like flashcards for in maths, just to know the difference between a type 1 and a type 2. That's the kind of thing that I think might be... Oh, sorry, I never actually wrote down the X bar thing there, but it's just that. Type 1 error is reject H0, but H0 is true. And then type 2 error you're about to see is the other way. If you get these wrong around, you're just going to score 0. So you do need to somehow have that sort of entire sentence memorized in your head. So reject H0, but H0 is true is type 1 error. So the probability of rejecting H0 is just the probability of being less than 328 and the probability of being greater than 332. And this distribution we're going to use is the same 330 and the same 8 because it's the same machine. But this time we're taking a sample of 55 rather than 25. So we've got a slightly different distribution to use here, but that's fine. It's just going to go in a calculator. And we literally just want to find the probability of being below this or above this, because that's the probability of rejecting H0. So we'll just get, and of course, because it's symmetrical, because these are equally either side of 330, it's just 2 lots the probability of that, which is that. And we'll be good to go with that bit there. And now it says mu is now apparently 325. Find the type 2 error. So that's accept H0, but H0 is false. So and this is in part A. So the probability of accepting H0 in part A will accept. Now we need to change because we know mu is 325. So it's the probability that we're bigger than this critical value here, which this was the value, remember, we agreed that if we were less than that, we would reject H0. So to accept H0, we need to be bigger than that. However, mu is now 325 because it tells us that. So we need to change our distribution slightly to make the mean 325, and now find the probability of being at this value here, or I guess 1 minus the probability of being less than it to find the probability of being over it, because if we're over it, then we're accepting H0. So I'm just doing 1 minus to get this flipped over in this distribution, because I know mu is now 325, and we end up with this number here as that answer there. Question 6, actually this ends with a couple of nice questions. Question 6 is just this. It says specify the distribution. That means you need to go to the formula book and you need to look at all your distributions, find PGF, which is at the last row, PGF there, and see which one of these does this look most like. And it doesn't really look massively like any of them, but it does look quite a lot like this because of the power to the r, and these are both power squareds. So let's just say it's negative binomial where r is 2, because we're squaring both of these. And then let's figure out how to make p such that this actually works. And it's not immediately obvious. I'm just going to essentially get rid of the 2's everywhere and just compare the things inside here. Initially, you look at this and think, well, p has to be 1 to make t equal t on the top. But that's not true, but partly because p can't really be 1, but also because then you end up with a 0 here and it just doesn't work. So you have to be a bit more intelligent. Firstly, you have to balance these two numbers here. They're the things that are constants, they can't change. So let's make this 3 and this 3 balance. So let's just times this entire fraction by 3 over 3. And now we can do some comparing. Now everything works. 3p has to be equal 1. And also 3 into 1 minus p has to be equal to 2. And if you solve those, you'll find that it's consistent for both p as a third. And so p as a third is what we'll use up there. And that will be the distribution that we'll have. A fair dice is rolled repeatedly. Describe an outcome that can be modeled using this distribution x. You just have to say something about how negative binomials work. So something with probability of third, and you're trying to get 2 of them. We saw that earlier with negative binomials. So I went with an unfair coin, probability of heads as a third, and you just need 2 heads. Something like that. I don't know how specific you have to be exactly, but just get the right idea. Okay, and next we're actually going to do some calculus, which is excellent. If you look deep into the formula book, you'll find this. It's very hidden away, but it is in there. E of x is this, and and variance of x is this. So all we have to do is differentiate this function here. I chose to do a bit of product rule just using a power minus 2. So this differentiates first for 2t, leave this alone, and then leave this alone, and differentiate this. Now that's a minus 2 times the inside of this derived, which is also a minus 2, so that's a plus 4, and then leave this alone with a minus 3 up there. So that's that. And yeah, then we can just plug in 1. They gave us a really nice one where as long as we plug in 1, all of these brackets just go away. And in fact, basically all of it goes away. It just ends up being 2 plus 4, which is 6. And then the variance, we need the double derivative apparently. So let's derive this again, which involves using, derive this again, derive g dashed. So let's do some more product rules to derive that, and it just goes away, and you end up with 2 lots of the rest of it. And then you derive this, which is again a minus 2 coming out. That makes a plus 4. So that's going to be a plus 8. So leave that alone for the still a t, and then lower that down to minus 3. And then do more product rule with this one here. That becomes a 2t, which makes this an 8t. Leave that alone. And then minus 3 comes down, minus 2 comes down. That's a plus 6. Times by 4 is 24. Leave that t squared alone and raise that to a minus 4 instead. And now let's plug in 1. Again, like I said, all the brackets just go away. So it's just the coefficients added together, 2 plus 8 plus 8 plus 24. Which is 42, and then the variance is 42 plus that 6 minus that 6 squared, which will give us an answer of 12. 7 marks for that, nice and easy. The discrete random variable is shown by this. Find the value of p of y equals 19. Now, kind of the whole point of probability generating functions, what's quite nice about them, well, there's lots of things that are nice about them, but one really nice thing is that the coefficients, when you write them out in like a polynomial form of like something t plus something t squared plus something t cubed, when you write them out like that, the coefficient of t to the power, let's say, n, is just the probability that y equals n. So what we're looking for here is we're looking for the coefficient of this function of t to the power 19. All right, so I need to write this in a form where I've just got lots of things added together and find the coefficient of t to the 19. Now, how do I do that? Well, it's because I can write this bit here as a power minus 2 and then do some A-level maths binomial expansion. Right? And then I can just write it out as the sum of a bunch of t's and just look for the coefficient of 19. So, okay, well, let's firstly, to use the formula that's in the book, which I want to use this. I need a 1 here. So I factorized out a 3 from this, but you have to keep that all to the power minus 2, then put the minus 2 down here to make a 9th. And now I can actually expand this. I'm sure this is probably how you learned it in regular maths anyway. And yes, now it's just 1 plus minus 2 times minus 2/3 to the 3. All of this object here is acting as the x. So I should probably say at this point as well, if I want the power t to the 19, I've already got t to the 10 here. So therefore, I need t to the 9 from this. But every time I take one of these things, I get a t to the 3. So I only need 3 of these things to get t to the 9. Combined with t to the 10 makes t to the 19. So I only need to go, I don't care about this term, that gives me a t to the 3. I don't care about this term, that gives me t to the 6. This term here gives me t to the 9 there, times t to the 10 gives me t to the 19. So I just need to work out the coefficient of this thing. That stuff will cancel, so it's just minus 4 times 2/3 to the power 3, which is this, and then times that by that 9th all the way over there, and the t to the 10 gives me t to the 19, and we end up with this coefficient here, which is our probability of y equals 19. And question 7, now most of this is about the geometric distribution function thing. But actually, you can just do this with vibes. Like it's actually a very straightforward last question. The first time on the fourth spin, well, that essentially one way to think about that is that you just need to dodge a red 4 times, right? To get to get a sorry, 3 times. You just need to dodge it, dodge it, dodge it, and then get it, right? So if you're getting a red on the fourth spin, it's just you must dodge it, you must dodge it, you must dodge it, probability 0.8, and then you must hit it, which is just this. You've got to dodge it first, because if you hit it, then you're not hitting it for the first time on the fourth spin. You might be hitting it for the second. So it's just dodge, 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 hit, and that's just that. For the third time on the eighth spin, very similar. All I'm going to say here is that I need to get exactly 2 of them anywhere in the first 7 spins, and then definitely get one on the 8th. So that's just a binomial, right? I need 2 reds somewhere in the first 7. So that's 7 choose 2 times 2 reds and 5 not reds. And that's going to get me 2. I don't care where those 2 are in the first 7 spins. That's going to get me 2 in the first 7 spins. And then just times by 0.2 again gives me definitely a red on the 8th spin. And I'll end up with this probability here. And then exactly 4 during the first 10. Well, that's just binomial. 10 choose 4. I need exactly 4. This to the power 4. This to the power 6. And that's exactly 4 in the first 10. Again, you could use more fancy distributions here, but just thinking it through is quite a nice way of doing it. And likewise here, you can use more fancy distributions as well, but it's actually not that hard to just think it through. R is the event, sorry, on this spinner apparently also yellow is 0.4. Doesn't really matter, but well, it does matter for this, but it doesn't really matter. It's the same spinner, because all we're going to think about is red, not red, and yellow, not yellow. So we're not thinking about the intersection between those 2 things in any way. R is the event the spinner lands on red for the first time in at most 4 spins. So all that really requires is that somewhere in the first 4 spins, I get a red. So the probability of that happening is just 1 minus the probability of dodging 4 reds in a row. Right? That's all that is. A red somewhere for the first time, somewhere in the first 4 spins. It's not saying on the 4th spin. It's saying somewhere in the first 4 spins. So I'm just going to find the probability of dodging red every single time in 4 spins and do 1 minus that, because that guarantees me all of the possibilities where a red appears at least once somewhere, right? And so that's just going to be that, nice and easy. And then yellow for the 3rd time in at most 7 spins. I'm going to do something very similar here. I'm just going to say to get yellow 3 times in at most 7 is just 1 minus the probability of getting none of them, minus the probability of getting 1 of them, minus the probability of getting 2 of them. That leaves me that just leaves me with all the cases where I have at least 3 in those 7 spins. So, well, okay, P of 0 is just 0.4 to the power 7. Sorry, 0.6 to the power 7, because I'm trying to dodge yellows, right? So 0.6 to the power 7 minus 7 choose 1. So this is just representing getting 1 yellow somewhere in the first 7 spins. This is representing getting 2 yellows somewhere in the first 7 spins. This is representing getting 0 of them. If I take away that from all the possible sample spaces, which is just this one, I'll end up with all the cases where I end up with at least 3 in those 7 spins. And that's just this probability here. And then P of R is greater, so R has the greatest probability. That's the whole paper. Thanks for watching, and I'll see you next time.